Hi guys. So we have one more session that I want to devote on introducing algorithms to you and pseudocode. And the more algorithms you see of rather simple problems, we'll later see algorithms of more complicated problems. But if I want you to design an algorithm and write a pseudocode for that algorithm, it's going to be of a more elementary problem of the same type that I will discuss in the lectures here. Now we're getting to these greedy algorithms which are already a little bit more sophisticated, as you will see. But we have one outstanding thing to do. I discussed with you the insertion sort, but we haven't looked at the way that it is implemented in pseudocode. So I remind you very quickly, the insertion sort, it was one of the sorting algorithms. We will see more, well, you see more in discrete math too, I should say, and much cleverer ones. But in this particular one, what does it do is, let's do it on an example, say k, x, b, let's put an a here, m. What you do is, when you have to sort this list alphabetically, you start with the second element actually. And you decide where does the second element go vis-a-vis what I have already. So in this case, the k would go behind the a. So the next step would be a, k. And then the remaining ones would be x, b, m. What is the result is that the front part is already in alphabetic order. Now it's not going to be the actual part of the solution, because there will be more letters will have to be inserted. But it is already ordered. In other words, if we keep doing this, at the end, everything will be ordered. So we now think, okay, where does x go? Well, x goes there, right? And then we have the two not used yet are b and m. So now we have to think about where b goes. So in other words, what we do is we really go check here. Does it fit here? Does it fit there? Or does it fit there? Okay? And we see it fits there, so we say, all right, so I'm going to put it there. So A, B, K, X, and then finally we have to put in M, and I hope that's clear, that will go here. So it seems like rather short compared to the bubble sort, but that's not really true, because this inserting here, since it is a small list, we see where this has to be done. But imagine that you have already, this initial list here is, say, 200 numbers, and now you have to figure out where this next numbering go into. It takes a little bit while. And there's a homework problem. I don't assign it, I have not assigned it, but you could look at it, where trying to find the position where this M should go. You can do that with the so-called version of the binary search, which makes it much quicker though. But, so let's do the original insertion sort, and so the procedure we'll just call insertion sort, but let's call it, insertion sort. I'm going to do caps here because otherwise it's not legible. Insertion sort. And so the input will be a list of numbers, A1, A2, AN. Well, it doesn't have to be numbers, right? It could be letters and so on. So I'm not going to specify too much here what this is. And so what we do, well, as I said, there's one loop that is going to loop through these various elements here, right? So this will be the first one, is the next one, is the next one, and the next one. And each time we decide where does this element go in the front list. Okay, so this means I'm going to loop here for what? There's a loop that has to describe here. I can do a while loop, but there's no reason here. Let's do a for loop. And so for, I don't know what to call it. Let's call it J. I'll follow the book a little bit so that it's from J from 2 to N. Remember, N is the length of the list here. And from 2, because we start with the second element. And what we do is we're going to compare it. So now imagine when you try to figure out what comes next, don't always look at the first part. Look somewhere in the middle. What is it happening in the middle? So we will have J will at this point, so for instance, if I'm looking in this case, what is J here? Well, this is J2, this is J4, 3, this is J equals 4. So this is the case where J is 4. That means I'm looking now at this element, and now I have to decide where does it go. How do I do this? Well, by comparing it one by one with the elements that already exist. So I'm going to loop again through this list. Now you can do this with a for loop. The textbook suggests the following, and let's see why not. So I'm going to write it this way. We start with 1. So we start, I is going to be the counter that will keep track on where in this front list we are, trying to fit in this element that we are working with, this jth element. So why do I do this? Because I'm going to keep going until I find something that is, so what I'm going to compare this way. I'm going to compare this, I'm saying, is this bigger than the first element? If it's bigger than the first element, I keep going. But once it's no longer bigger than the first element, I know that's where it should, let me say. I'm going to compare this with the various elements in this list. I'm going to compare it with the first element, the second element, and in general the ith element. If this guy is bigger than the ith element, I know I have to go to the next element. So I'm going to increase my I. If it's smaller than it, then I know that it has found its spot. Okay? All right. So, and therefore I'm going to use a while loop. I'm going to say while this element is bigger than whatever I'm checking, I have to keep checking. Okay, so while, let's write down exactly how that would come with the counters, while aj, that's the element I'm trying to match, is bigger than ai, that's the element that I am looking at in the front list. Remember this I here, this counter? So this counter keeps track on where in this front list I am trying to match my element, my aj. Okay. So while this happens, while aj is bigger, I know I have to keep going. So I is I plus 1. So I start increasing I, because at some point, okay, let's see. At some point I have to get bigger, right? This element will be bigger, even it could be that, like for instance in the case of x, it happens all the way at the end, but it's going to happen. So what I have to do then? So let's look at this situation, perhaps neither one is really good. I'm gonna let's concoct a situation a little bit more general here. Okay, my example was not the nicest of cases. Also, I want to do a little bit better. So suppose I have already found this list here, and the purpose now is to inject e there. So this is the element here. I'm going to look at I is 1. Is it bigger than? No. So I keep going. Is it bigger? So now I increased I. No. Is it bigger than it? No. So I keep increasing my I. So I keep doing this because the while condition is still valid. But now the while condition is no longer valid because this E is now smaller than G. So what needs to be done? Let's think about what needs to be done. What needs to be done in this case is E has to be inserted in the existing list X. Now that itself is a little bit annoying to do, so I'm going to pretend that I have another procedure that I have already designed to do that. And so what I'm going to say is insert. So this is when the while loop stops. So I have to go now indent in the same part here, right? So so insert aj in the ith. Let's think about this. So I at this moment would be 3. I'm thinking, is it the ith or the I plus 1 spot? I is 3, and so this has to now be inserted in. So remember, when I was doing this, I was 3. In the last comparison here, I was comparing E with D, that was with the I was 3, and I said, okay, it's still not true, so I increase I. So I is at this moment 4. When I check this, I is 4, and that is exactly the position it should be. So it is the ith spot. Now, or perhaps insert is even a little bit worse. Because it's not even inserting, I have to then also delete it from my the rest of the list, although that's not really important because since this is part of this loop here, the next case will be when the whole loop is carried out, j will be incremented by 1. So this is, I'm not going to touch this here anymore. So this is fine enough. I could, instead of insert, I could say move aj into the ith spot. Now I agree that this itself needs to be implemented, and in fact the textbook does that, but as I find it something that it's kind of clear what should be done. It's not a huge thing here, right? It is just make spot, shift everything up a little bit to the right and give this E a spot to move in. It's very clear that this can be done, but it is a bit tedious to do it because you have to keep track with the counters and all that. And if you look at the textbook's algorithm, you see how it's done. But so that's it. I'm done. Because if this loop is finished, that means that all the elements have been inserted into the front in the right spot. And so we can say, sorry, return. And what we return? Well, A1, A2, AN, because that will now be the list that is listed in increasing order. Okay. So this is not yet a greedy algorithm. So let's now talk about greedy algorithms. Now, the term is, it's not always entirely clear what we mean with a greedy algorithm, but in many cases it is kind of obvious what is meant. It's a little bit of a subjective term, but greedy means the following. There's a problem that we have to solve, and there are often problems don't have one solution, they have many solutions. And what we want to somehow find is the optimal solution. And let's work on a problem. I'll give already the problem that we will discuss here is the counting change, or not, yeah. How they call it here? Change making. Making change. Change in the sense of coins. So we have coins, and let's just assume we have the regular coin. We have a quarter. We have a dime. We have a nickel. And we have a penny. And now I have to pay a certain amount in, you go to the grocery, it comes out to be $75 plus $36 cents. So how do you pay the 36 cents? Okay, the dollars that you do with bills, but how do you pay that? Well, an optimal one for us, well, that's the thing. First of all, what is optimal? That depends a little bit on what you say. For instance, optimal might be that I want to get rid of as many coins as possible. So I want to make as much change as possible as what I have. But here we're assuming that we have unlimited amounts of each of these 4 coins, and we want to make a change using as few coins as possible. Let's call that the optimal change making in this particular case. But I'm saying this is not the only way. You could envision a better optimal one. You could say, okay, I want to optimize something else, like I want to use the heaviest coins first, although that comes down almost to this. That comes down to the same thing in this case. But you can imagine there are other optimizations that I can think of, and we'll see in the next example where there are different choices you can make. So we were trying to find an optimal solution. But it would already be good to find a solution. Now, of course, there's an obvious solution. If I have to make a certain amount of change, just pay that many pennies. So there's no need to write an algorithm if that's the only thing you want to do, because it's just pay everything with pennies. But if you want to optimize, you might try to strategize differently. Now, what is a greedy algorithm? So this is one thing. We want to optimize a solution, but that's not what greedy algorithms are. Greedy algorithms is somehow a naive approach to this, and it says, I'm just going to get rid. In this particular case, let's formulate it in this case. I said because it is something that is a little bit subjective here. What is greedy here? I'm going to try to pay with the highest denomination first until I can no longer, and then I pay with the next denomination, and until I can no longer, and then with the nickels, and if that's not, and then is everything left, then I'm going to pay with pennies. Okay, so that is the greedy part. In other words, but why? Because of course the least amount of coins. suppose you have to pay $1. It's clear what the least amount of coins are if you have to pay $1, 4 quarters. So that's why I'm trying to pay with quarters first. So I'm always going to try to pay with something that I think will give me the least amount. Now, just thinking that at each time it will give me the least amount is not necessarily ensures that it is the least amount that I will get. And that is the difference between a greedy algorithm, which just says, okay, in order to solve this, I'm just going to try to do what looks the best optimal thing at the time. But it's very strange. Things can happen. And we'll see examples of that. At each time you think, okay, this is the optimal choice, so I'm going to make it. This is the optimal choice, so I'm going to make it. That's the greedy algorithm. And the expectation or the hope is that actually this gives you the optimal solution. Now you say, Professor, you're saying it yourself. Each time you're using the optimal solution. Why would that not be the best solution? Okay, I'll give you an example later on, but I want to first implement this particular algorithm here, the greedy algorithm of the coin chains, making coins. And so how would it work in general? So I'm going to actually make, first of all, I am allowing myself different denominations. It doesn't have to be cents, that 25, 10, 5, 1 cent. That could be in Europe where they have different coins, or it could be just an invention. I could play some Monopoly game where they have weird denominations. So let's make it very general. So the procedure I'm going to call, I'm following the book, it's called change. And what it has is, it has denominations C1, C2, C3, up to, and they say CR here. So these are the denominations of the coins, if you want. These are certain amounts. And then X is the amount that I want to make. Or they call it N here. Well, I'm going to call it X. So these are, let's call this the values of the coins. Or stamps. It doesn't have to be coins, it could be stamps, it could be chips, it could be anything, right? Like, for instance, if you're playing poker, for those that play poker, you have different kinds of chips, and you have to pay the guy some certain amount. You're gonna try to use your bigger stack so that you don't have to start moving too many chips, right? So same thing, and you could have chips of very many different values. And the question is, and this is the amount that you want to make. Okay, so how would this work? Well, I'm going to go through all my counts. I'm going to try to, so the greedy part says at each given time, try to pay with C1 until you no longer can. Then go to C2 and try to pay until you no longer can. So we're going to loop through the CIs, and notice that they have already been ordered. You might say, well, perhaps they were given to us in a different way. Well, then you do one of the sorting algorithms from before. You sort it and then you apply it. But notice that the sorting is kind of backwards here. It's from the biggest to smallest. But again, let's assume that we have this already finished. So, okay, we loop. It's a loop for I from, let me do counter, I from 1 to R. So I will go through, so here this will be I1, this will be I2, this will be I3, and this will be I4. These are the four. In this case, so this would be C1, this would be C2, this would be C3, and this would be C4. And now what I'm going to do is pay. So I have this X, and I'm going to see, can I pay with C1? So as long as I'm above, if X is bigger than C1, then I can use C1 to pay with it, and what's the new amount is going to be X minus C1, okay? The only thing I need to take also into account is I kind of have to register how many times I use each coin. So how many times I'm going to use C1? Well, before I start, I don't know. Perhaps the amount is too small. I can never use it. So the default value, D1 or DI, so the DIs is going to be the number of coins of that type, of type CI. Okay, so how many times I'm using it, and so let's do it on an example. Let's do the example, let's do, I don't know, 67 cents. So X is 67 here, X is 67. Okay, So if x is 67, I obviously, so okay, as I put di equal to 0 at the beginning. I'm somewhere in the middle now, but we have to start, right? So that's, you have to think we have already perhaps used quarters and dimes, and now I'm using nickels. So when I start, I'm think perhaps no nickels are needed, and if I see otherwise, then I change and I will add increase this number. Okay, so and now I'm trying to, what I'm going to do is the amount that is left, I'm going to start subtracting. I'm going to, let's say we are I is 3, we're going to compare it with 5 cents. If it's bigger than 5 cents, then I subtract 5 cents from it, and then try again. So it is a while loop here. You could do it in a for loop, but it is much nicer to do it in a while loop, namely, while your amount that you have x is bigger than the coin that you're trying to pay with at the moment. Okay, at the moment, remember, this is the coin CI you pay with. While this is true, perhaps equal to, because if it's equal, then you just pay and you're done, right? I'm gonna use that, and it means I'm going to use that CI coin, so that the count goes up by 1, and the amount goes down by the amount that I just paid. CI is the coin. So let's do this. Let's do this for 67. Okay. So we start with I is 1 and D1 is 0. So as long as x is bigger than C1 is 25, I will do this. So, okay, so the first time I'm going to see what are the various steps here that will happen. So, okay, so this is I. Oh, what is that? This is I. Here is, I'm going to write I. Here I'm going to write di, and here I'm going to write x. So before I start, so let's say I is 0, that's before anything starts. Oh no, well, right, before, okay, let's start with 1. I is 1, then at that, and originally I put di equals 0, and x is just the original x that I had, okay? So, now I'm doing this. While x is bigger than ci, well, ci at c1 is 25, so is 25, sorry, x is 67, right? Sorry, let's put in the value here. I don't know why I put x, I meant the value, 67. So I'm comparing. Is x bigger than c1? Yes, it is. So I'm gonna upgrade this thing, and I'm gonna change. These two things I'm gonna change. So let's see. This is now 1, and therefore now I subtract 25 from here because I paid already once. So that is 42. Now the condition is still satisfied. 42. So remember, this is the question here: is this bigger than C1? Is this bigger than 25? Is this bigger than 25? Yes, this keeps being. So as long as this is the case, I is not going to change. So I'm going to again take a 25 coin, and then is left is 17. Is this bigger than 25? No. No longer case. This means, therefore, I'm going to increment my I. So we have we done this? Yes, that is happening because this loop has now been carried out. This condition is no longer done, so this is carried out. This means the loop says, okay, increment your I. So we go to 2, and we start all over again. 2 tells me, the first command is to put D2 equal to 0. Okay, and now I'm going to compare with 10. That's C2, right? C2 is 10 cents. Is 17 bigger than 10? Yes, it is. So I'm going to subtract. I get, so this is 17. Okay, so if I do this, I get 1 coin, I subtract 7. Is this bigger than 10? No. This means, again, my while loop is finished, and my I will increase to 3. And now I'm going to compare this with nickels. At the beginning, I don't know that I need any nickels. And the question is this bigger than 5? The answer is yes, it is. This means I'm going to increment my number of nickels that I need, subtract this amount. Is this bigger than 5? No. So I'm saying, okay, I need to go to the next coin available. And so now we start normally. This is how we start. We compare this with 1. Is this bigger than 1? Yes, it is. So we increment. So subtract the number, the amount, that is in this case also 1. Is this bigger than 1? Yes. So we do again. We put a 2 here. We subtract, that's 0. Is this bigger than 1? No. And there's nothing else to be done. I run through everything, and this is 0. So this algorithm gives all the correct answer in this case, right? So we see, so what is the conclusion? We need 2 quarters, 1 dime, 1 nickel, and 2 pennies. And you can verify that is correct. And also, and this is more amazing, is this actually is the best solution. Okay? Now, there's one thing I have to say, and that is some omission in the book, is this might not work. Suppose there were no pennies. Suppose I could only make change using 25, 10, and 5 cents. Then at this spot here, I would have been done, right? At this spot, I would have been done, because the last coin, so remember, can no longer use pennies. The last comparison I could do with nickels, can I pay nickels? The answer is no, so I stop, because this R is now only 3, and there is not this doesn't exist anymore. But look, I have still an amount left. So you see, this doesn't always have a solution, and therefore, and this is what is forgotten, one has to check here. If x is not 0, then you have to say something. Then say fail. I don't know, then say fail, then return fail. Let's write it that way, okay? I'm going to write it that way. Then the return fail. Else return D1, D2, all the way up to DR, the number of coins that you use for each of them. But there is a situation where there is still change left, but you cannot make it anymore because you don't have the right coins. Okay. That's something that was missing in the algorithm in over there and in the textbook. Now, to come, is this the optimal solution? I'm not going to discuss this in too much detail, but if you think about it, how can I happen, for instance, in the case of the nickels here? You see, the amount, when I start looking at nickels, it has to be less than 10, because otherwise I could a dime, and it has to be more than 5, right? Now, that's just a very small window in which I can use a nickel. Namely, it could be either 9, 8, 7, 6, or 5. These are the only amounts that I'm going to be the amounts that I can start that use the nickel. And if I use the nickel, I can, whatever I subtract from 9, 8, 6, 7, or 5, the result is always going to be smaller than 5, so I will no longer use a nickel. So I can use at most 1 nickel in this case. Okay? But there are a couple of other things that you can do. You can never use more than two dimes and a nickel. Because if you use 2 dimes and a nickel, that means you had 25 cents at that moment. But if you had 25 cents, you could have used a quarter. Your algorithm would have forced you to use the quarter instead of these two dimes and nickels. So you see, we can never have 2 dimes and 1 nickel. Now, that's okay. We have only 1 dime and 1 nickel. So in this particular case, it worked. It was correct. And reasoning like this, you'll see this is the optimal solution. Now, I want to show you that it is not this optimal solution. Suppose here, so let's give an example. There's another examples in the textbook, in the homework that I'm going to give you. But suppose C1 is 25, C2 is 10, and C3 is 1. So in other words, no nickels. Suppose they say, okay, there is a shortage of coins, by the way, out there. So they might say, okay, sorry guys, there are no nickels anymore. You can have to pay with either quarters, dimes, or pennies. Now imagine you have to pay 30 cents. So what is your greedy algorithm saying? Your greedy algorithm says, okay, 30 cents. So we're going to try to pay this. So in other words, we apply now this algorithm that we designed here, change, with C1 equal to 25, C2 equal to 10, and C3 equal to 1. Okay? So R is 3, there are only 3 coins. Now if you do this, think about it, you're going to be able to buy a 25, so say, okay, I'm doing that, and how much is left? 5. Okay, 5, the only way I can pay 5, since I don't have nickels, is with pennies. So 1 plus 1 plus 1 plus 1 plus 1. So I have 1, 2, 3, 4, 5, 6 coins. Now, do you think, is this the optimal solution? No, it isn't, right? Because I could could pay it this way. And that is less coins. So you see, although I did the greedy way, so this, think about this, right? And let me go over it again. 30. What's the optimal thing I can pay? Optimal being the biggest one, so that the more I pay, the less coins I should be using. That's the idea, right? So I'm using the biggest coin I have, 25. Okay, I've paid that, and now I have 5 things left. The biggest coin I can use at this moment is only the penny, and I have to use it 5 times. At this point, I have no choice anymore. So you chose at every single step the best solution, yet it is globally not the best solution. And this is something you have to start realizing, and that is one of the big complications that we face, and that we will discuss in discrete math in other situations as well, is that optimization can be very, very difficult, because just optimizing at each step doesn't guarantee that you have actually the best solution. This might sound weird, but if you say, I don't believe it, just look at this here. This tells you that this is something going on here. Okay, so moving on, I want to do one more problem, and let me see. I'm going to see whether I can make. No, how do I do this? So I want a different type of paper. Okay, I want this kind of paper. Yes, because I'm going to work on something. Scheduling. So the scheduling problem. And it is the easiest if I do it visually. So I have a scheduling problem, and the problem is the following. I have a lecture hall, and I have a bunch of talks, a list of talks. And so I'm in charge of this lecture hall, and people and the organizer of this conference says, okay, these are all the talks. What can you put in your lecture hall? And so how are the talks listed? Well, it has a beginning time and end time. And of course, if you have in a hall, there cannot be 2 talks at the same time. We're going to be doing something perhaps a little bit silly, is saying if one talk's end, right then we can start a new talk. So although this is not really, perhaps logistically might be difficult to do, but okay, we don't care about that. Suppose it's virtual, we have projections that come up, or movies, and that can be done in an instant, right? So, okay, so here's an example of, I'm gonna list here on a scale, let's see, I want to take here, let me take an example here. The book doesn't have very nice examples, unfortunately. Let me make up an example, and then we will work on, we're going to have to do several examples. So here's my timeline, and it's, let's say, from 8 a.m. to 12 p.m. So I'm going to divide every hour in 4 quarters, right? This is 9 a.m., this is 10 a.m., this is 11 a.m., and this is 12 a.m. Perhaps I should do a little bit more. Allow me to actually, otherwise it's going to be very cramped. So let's do it this way. Let's put this 9 a.m. here, and then this would be 10 a.m. and so then 4. This would be 11 a.m. and then 4. See, it fits perfect. 12 a.m. Okay, and so here are the talks. And the talks, I'm just going to list the beginning and the end point. I'm just making it up. So this is talk 1, just let's number them. This is talk 2. I'm going to have talk 3 here. And this is going to be talk 4. And then I need more time, more space. I'm going to erase these guys a little bit, okay? Myself a little bit more space here. Let's do type. And then we have this talk here. Let's type this talk. This is talk talk 5, and then let's say to this talk, this is talk 6, and then one more, let's say this is talk 7. Okay, I only go until this 11 o'clock, so it doesn't matter, but here. Okay, and what is the goal is to schedule, this might not be a good choice, but schedule as many talks as you can. Let's put another talk in here. Let's put here the talk 8. Okay, I'm going to try to put as many talks as possible. Okay, so the idea to optimize, and there might different ways of optimizing, okay, but what I'm now claiming, what I'm saying is I want to schedule as many as possible. There could be different things. I could say, I mean, each talk might have a number of attendees, and I might optimize the number of attendees, because perhaps talk 1 is a long talk, but there's only 5 people coming there, so why would I want to schedule that if there's other talks with much more people coming, okay? That's a different problem that we will discuss in discrete math too. But for now, we just take the simplest optimization that we can think of is as many as possible. So we can do, we can have various strategies here. What is the greedy? What is greedy here? And that's why I'm trying to say greedy is a subjective thing. I can say, well, let's start. It sounds like I should schedule the one that starts the earliest first, right? That sounds like to me that I should do. So let me put another one here just to get a little bit more. There's no reason in which order I listed the talks, by the way. I should mention that. The textbook talks about that, but you'll see, I'm going to do a different solution than the textbook, and mine will be actually nicer. So let's put this talk, let's put also this talk in here. 9 and another talk 8, yeah, and then do this talk 10. Okay. All right. So again, let me get rid of. I made this a bit small. Let me make this a little bit bigger, then I can do this quicker. Okay. So the first thing I could say is I'm going to take the earliest talk I'm going to schedule first. And then I'll see what is the one that I can schedule next. Of course, so we have this notion of one talk being compatible with the schedule, meaning that it fits in the schedule, meaning there is no other talk that it overlaps with. Okay, so we're trying to build a schedule. So the schedule we build is S is going to be our schedule of the talks that we want to put in. Okay, if we do the earliest time first, I'm going to put one more in just for the heck of it. So let's do also, let's put in this talk here, talk 11. If I put a little bit more in, then you see nicer things happen. So the schedule, let's say, I'm going to, one that starts first, that would be 2. So beginning times. So my greed is, my greeding, I'm greedy as far as starting times will come. I want to start as early as possible. That seems to be the best greedy strategy I can come up. It actually isn't, but we'll see. Start time, beginning time. Okay, so what would I put first? Well, 2, right? I would put 2 first because 2 will, so now I have to, let's see how I'm going to do this without erasing. So 2 would start first. And now I look at what's the next one I can use to cover what is still compatible with 2. It's clear that some of them are no longer compatible. They overlap with 2, so I can, what is the earliest starting talk that is still compatible with 2? That seems to be 5, right? Okay. Now, okay, I'm going to cheat a little bit. Sorry, I made this examples like a little bit. I'm going to make 5 to be really long, and then you'll see immediately that something is going wrong here. So 5 is this long. So, okay, so sorry, 5 is now goes all the way here. Okay, that's it. That's it. I can only schedule 2 talks. If I use this strategy, then I can schedule 2 and 5. You say, Professor, I know, of course, that's not smart. We should take the shortest ones. I try to always take the shortest one, okay? All right, okay, let's do that. So let's try to do that. So I'm going to schedule, so this is beginning time. So here is the time of shortest. Okay, so I'm going to try to erase this red, hopefully not erasing anything else. Okay, okay, okay. So this, now I'm going to use red again because the shortest. What is the shortest here? The shortest talk seems to be talk 9. Right? So I'm going to take 9 first. Okay. 9. And then what is still compatible with 9? Now we have to, and what is the shortest time that is compatible with 9? Let's see what is no longer compatible with 9. So perhaps I should make those red and the other one, okay, sorry, I'm going to change my mind. In green means in, right? That should, okay, let me do it this way. So this is green. 9 is the shortest talk. And red will be now those that are no longer compatible with it. Okay? So let's see what I have to rule out. Well, I have to rule out 10 is no longer compatible. 11 is still. 2 is no longer compatible. 1 is no longer compatible. That seems to be it. Okay. So now what's the shortest that remains? 6. You agree with me? Okay, 6. If somebody is yelling, no, I don't agree, I don't hear you. Sorry. So I'm going to take 6. So 6. What is now ruled out? Oh, that has to be in green. That has to be green. Sorry. So this is green. So what do we have to rule out now when we schedule this one? Well, we have to rule out 7. We have to rule out 5. We can no longer take 4. We cannot take 3. But they all overlap with 6. Okay. So, right. So what's the next smallest talk I can take that is still compatible? I'm going to cheat a little bit. I'm sorry, guys. I just want to make things happen that you see. So this 8 we have not used in the previous thing. Suppose 8 was here, actually. This was 8. Okay? So even 8 has been ruled out now by the way that I moved it there. So, oh, this was to be this one. 8 is also ruled out. So what is still left? The shortest talk that is left, well, there's only one talk left, that is 11. So the next one I can put in is 11. And so this is how my schedule looks like. Here's green. So these two talk, 9, 11, and 6. But they're all so short. Do you think this was the best choice? Now, in the textbook, they give other examples where it shows it's absolutely not the best one. Imagine this. You have a very short talk that it goes, say, from 10 to 10:15. But all the other talks go either past 10 o'clock or start before 10 o'clock. That means if you take that shortest talk, it overlaps with everything else, and therefore you cannot schedule anything else anymore. So being the shortest is not the best choice. And now comes the strange thing. I'm going to choose something that works. I'm going to start with the earliest end time. Okay, so I have to erase. Hopefully I don't get rid of too many things that I don't want to get rid of. Cool, huh? That I can do this. The program I use is Notability if you want to use something like that. They have to pay for, it's a registration fee that it has, but okay. Okay, so end time. I'm going to look at the talk that finishes first. The earliest finishing talk. Let's see, what is that? That seems to be 9, right? So again, we do this 9. And now I have to, everything that is no longer compatible with 9, okay, that cannot be scheduled anymore. So that would be this guy, 10, 2, and 1. Okay, you say, oh, Professor, I don't like it either because you have now ruled out quite a lot. But okay, let's see, 9. What is now the last, the end time of the remaining ones, which ends earliest? The earliest one that ends is now 11, right? This is going to be the earliest, right? It doesn't look like, okay. So now 11, okay. This seems to be the same schedule that I have so far with the shortest, but you'll see it will get better. So, okay, so this has to be in green. So this is my talk. What is ruled out by taking 11? Well, what is ruled out is 4 as well as 3. But that's it. 5 is still compatible, 6, 7, and 8 are still compatible. Okay, so again, what of the remaining ones ends first? 6 ends first. Yeah, it doesn't give, shoot. Yeah, I'm sorry, this is not, it's not giving me a better solution. It should give a better solution, but okay, I cannot mess with too many okay, let me stick, I want to change 7. Okay, we have not really used 7, so I think it's allowed. I can change 7. I'll make it long enough so that it would not occur in my previous guy. So remember, in the previous counting, when I talk beginning time 7, I never used 7 because it never came into the being, because 5 ruled almost everything else out, right? So I never considered 7. So 7 has never been used yet in this scenario. In this scenario, did I ever use 7? No, because there were always shorter ones than 7. So again, I can change 7 without changing what happens here and what happens there. But now something happens here. Sorry, I didn't prepare it well, so I didn't really try to find the best one. So let's see. What's the earliest end time available? That is 6. No, yeah, you might still protest against this because okay. I gave you an example where the shortest does not give the optimal strategy, right? And this particular one, actually, it seems to be doing it the way that I now draw it. Yeah. I can change it still, you know, but okay, I can add one more talk to it. You might, okay, don't scream and yell too much. Okay, guys, I'm gonna add this talk 12. Again, I'm claiming this talk will never have, in my previous cases, it would not been considered, because in the previous case I took 5 as the one that starts earliest. Well, 12 and 5 stay in the same time, so, but there was no strategy in which to choose, so I chose the first one I saw. So I choose 5. Right. Okay. And therefore, okay, if you don't like that idea, so let me change 12 slightly, and I'll make 12 start here. So then I would never have chosen 12. It was also not the shortest. When I had chosen shortest, I had to choose 6. But 6 and 12, oh, 6 and 12, no, it's okay. So, sorry, 12 has to go up to here then. I'm sorry, I'm trying to give an example. Now you have to check it, right? Because I've changed so much that now things might be a little bit. Okay, so this should be 12. Let's see. As I said, in this scenario, 12 would never be considered. In this scenario, once I had chosen 6, I could not choose 12 anymore because it conflicts. So again, I would not have chosen 12. Now, okay, in our scenario, where are we now? Okay, sorry, this has to go now, this 6. Because 12 ends earlier than 6, so I should have put 12 here now. Okay? In this scenario, I'm going to, the talk that ends first of all the remaining talks is 12. So this would be now in green, right? So this is green. Here is green. And what is ruled out now by taking green? Let's see. I can no longer do 6 and I can no longer do 5. But I can still do 8 and I can still do 7. So you see now, okay, I hope you double check that what the new picture that I have, everything is still true what I wrote down here. 8 is the one that ends first, and therefore I should pick it in my greedy scenario. Okay, so I pick this one, but now of course this also rules out 7, and there's nothing left anymore. So here you see we do have 4 in the optimal strategy. Okay, so I want to quickly now give you the pseudocode, and as I said, it is different than how the textbook does it. It's much nicer. I didn't come up with it. I found it somewhere online as well, and therefore it's already a bit clever, right? And you see it's clever also in the sense that because we have 3 different ways of being greedy, we don't know which one is the best way. Now, this is a bit, again, textbook explains it, this actually gives always the optimal solution. And I want you to look at the textbook to find out what it is. I'm not going to, this is not really what we want to do here. This is, I think, beyond an introduction to algorithms to show that this is that this actually is an optimal solution. That this algorithm, where we always look for the time, the first time with the earliest end time that is still available, gives you the optimal solution. And this is perhaps something counterintuitive, right? I'm saying you would first go for this, and this is perhaps something you would never think about. And okay, and this is a real life problem, scheduling. I don't know if you've ever been in an organization or something, or if you had to schedule exams or lectures or something like that. This is quite cumbersome thing. Okay, so what's the algorithm go? Let's write it down. And so the procedure. I call it Hall scheduling. No, schedule. I just call it schedule. Sorry, this is something else. Schedule. And so what I'm giving is a list of talks. And so these are a list of talks. They are not ordered by any way, but a talk is actually, that's a pair of a beginning time and an end time. So this is the beginning time, and this is the end time. These are the two things I need to know. But I don't even specify them. I'm saying the talks, let me not even mention that. Just say, how are the talks given to me? Well, they have a beginning. And what I know about the talk is when it begins and when it ends. Okay, so here's what I'm going to do. S is going to be the schedule that I make. So S is my schedule. So it's the schedule that I'm going to come up with. And of course, in the beginning, I might not be able to schedule anything, so I'm going to put it empty. For one thing, if the input would have been an empty list of talks, then the schedule would be an empty set. So I have to, that's clearly the default value here. But of course, the whole purpose is to try to change that. And so what I'm going to do is now, I'm going to try to find talks that are compatible using my greedy strategy. So while, as long as there are talks available, so as long as L is not empty, I'm going to choose talk T in L with the earliest end time. So now this is something at the moment you don't know, you haven't seen the rest of the algorithm yet, but what I'm thinking here, let me say, I should perhaps have said it before I write down. What I'm thinking of is doing the following is what I did here too. Is basically the green and blue. So I'm finding the one that fits earliest, with the earliest end time. That is when I made my green choice. And the next thing I did was the red ones. In other words, scrapping out the things I can no longer use. So in other words, I'm going to reduce my list L. I'm going to throw these talks out. So L is going to get smaller and smaller, and eventually it will become 0. Okay, so eventually it will become empty, and then the whole thing stops. Of course, if this never happens, then this program hangs. That's something we don't want. So choose a talk T with earliest end time. This exists because it's a non-empty set. So there's always one, if there's only one, that is the talk with the earliest end time. Okay, so what do I do? Well, a couple of things happen now, right? Because this talk should go into my schedule. That is my greedy strategy, is taking this time and put it to the schedule. So let's do that. So S becomes S and adjoin my talk T here. Okay, so this is the clever thing to do, is add T to it. What should I now also do? Well, I have to do now the red strategy, remove all the talks that are incompatible with the one that I just chose. In particular, also remove it itself. Incompatible meaning there's an overlap. And an understanding is that the talk overlaps with itself, kind of, right? So remove from L all talks incompatible with talk T, including T, but let me not write that down. So I throw out a bunch of things, and it could be that I throw out everything and then it's empty, and then the while loop stops. And if it's not empty, the while loop continues, and I take the next available time with earliest end time. So I do exactly what my greedy strategy tells me. I will come up with this list of talks as long as this while loop is not finished, and once the while loop is finished, there's nothing to schedule anymore, and the answer will be exactly that. All right. So very compact, very nice procedure, much better than the one they give in textbook. And in fact, I think that there's mistakes in the one in the textbook. There's some weird things about these inequalities that they use that I think are incorrect. All right, that was it for it. And so I'm gonna assign homeworks that are gonna test these procedures. You're gonna have to apply them yourself, figure it out yourself, just to get used to them and discuss. Okay, you'll see the homeworks are actually easier because I cannot expect you to design greedy algorithms, because they are, as you see, not so obvious anymore. They're somehow even sometimes counterintuitive in the sense here, why would you have chosen this instead of beginning time or shortest time? And also here, why is this the optimal strategy, and is it always the case? And I should have said this. For our coins, existing coins, this is the optimal strategy, but I gave you an example. I erased it because I needed more space. I gave you an example where this is not the optimal strategy if, for instance, if you don't have nickels. So a greedy algorithm is not just always optimal. It might be optimal for certain situations and not optimal for others. Okay? So weird things happen, and it makes it that's why greedy algorithms is a much more complicated subject matter, and therefore I'm not going to expect you to come up yourself with these things. All right.